Our last video is about LeChatelier's principle. You should already be able to define and describe equilibrium reactions, but now we're going to use LeChatelier's principle to qualitatively determine which way the reaction will shift to restore an equilibrium. We've done these problems at the beginning of the unit, but these are going to be really stylistic. You need to make sure you're writing your answers in a specific way. So back to that phosgene gas, we're noticing that the phosgene gas is kind of hard to manufacture, so there has to be some way that they manufactured it because otherwise it stays really reactant heavy. So we're going to get to that using LeChatelier's principle. If a change is imposed in the system in equilibrium, the position of the equilibrium shifts in a direction that tends to reduce the change. So if you add something to it, it's going to reduce the addition, or if you take away, it's going to put back and restore. The Haber process is the most familiar example of LeChatelier's principle, where nitrogens are combined to form with hydrogens to form ammonia that's used in agriculture. So if you had an equilibrium condition and a scientist goes in and add more hydrogen at that time, you should notice there's a huge spike. That means the reaction will reshift. What will do, it will use the hydrogen to bombard the nitrogen. So notice that those both decrease because they're both reactants. And they'll form more ammonia to restore an equilibrium. The equilibrium is never the same equilibrium as you started with. Notice that the values are all changed. But the K expression that you would have written and that value will calculate the same. They just have to reshift their equilibrium values. So the rules were if a species is added, the reaction shifts away from the species to restore it, and if a species is removed or taken, the reaction will shift towards that species to restore it. In terms of changes in volume, a decrease in volume increases the pressure and causes a shift to favor less moles since there's less room. An increase in volume decreases the pressure and causes a shift that favors more moles of gas. So in an equation like N2O4 is reversible with 2NO2. If you increase the volume, that means they have more room. You'll favor the side which has 2NO2 because it has more moles. It shifts to the right. If you decrease the volume, it has less room. So you're going to favor the side that has less moles, which is the reactant side of N2O4 since there's only one mole of it. And in a pictorial sense, if you had, let's say, 2 reds for every 1 gray and it's reversible, at first it looks like there's quite a bit of red, and as you increase the pressure on it, there's less and less red because you're going to shift to make more gray since it takes up less room since there's only 1 for every 2 reds. For changes in temperature, it really depends on where the heat is. So if it's an endothermic reaction, the heat is reacting with the reactants to form products. If it's an exothermic, it's produced in the products. So reading it backwards, it's going with the products to make reactants. And so you're going to consider it just like a reactant in our products. A catalyst will not affect the rate of reaction will not affect the equilibrium because it affects both rates equally. So if the regular forward reaction is in the purple and the reverse also in the purple, the green represents what would happen to the activation energy if a catalyst was added. Notice that you're going to go forward just as much as you're going to go reverse. The rates are going to be equal still. If a common ion is added, you're shifted away from that ion. So this is a little bit more detailed. If they didn't say sodium chloride was in there, but you have to notice that it's similar to sodium, just ions, because sodium chloride, once it hits that water, will form sodium separate from chloride ions. So that means you're essentially adding sodium to that substance, so you'll form more sodium fluoride since it's going to shift to the right. And something similar with removal of ions, which is a little harder to see. In this reaction, if hydrogen ions were added, how will this affect the equation? And most people will accidentally write that it will not have an effect because there's no H in the equation. But the problem is H positives like fluoride ions, and that will form a covalent bond which will not necessarily dissolve. It will take out the F, and then therefore the reaction will shift to the left to make more reactants because you're taking out the fluorides by adding in hydrogens. So let's see a few more examples that we want to make sure we're writing in a specific way. Here's the normal Haber process, which is exothermic, and we want to know how hydrogen would be affected by the following. Maybe pause the video and see if you can get the same answers as me. If ammonia is added, I'm going to increase the product side, and therefore there's going to be too many products, and shift to the left to increase more hydrogens to compete with it. So hydrogen increases. If nitrogen is being added, it will react with the hydrogen, so it will decrease. Heat being added means we're going to increase this 92 kilojoules. It will decompose the ammonia and read it backwards. That will form more hydrogens. If you pressure decrease, that means that you're letting the gases spread out. That means they have more room, and so you'll favor the side with more moles, which is the left with 1 plus 3 moles. The right only had 2. So I'm going to favor the left side by forming it, and the hydrogen will increase. Ammonia being removed means that you're going to take out ammonia as it's produced. The reaction will think that there's no ammonia. It will restore the ammonia and by using the hydrogen particles, so hydrogen will decrease. If nitrogen's removed, it will need to form more nitrogen. By default, if it forms nitrogen, it also has to form hydrogen, so hydrogen will increase. And last, decreasing the volume means you have less moles because you have less room. Less moles was the right side. In order to make the right side, we're going to use up the 3 hydrogens, and so hydrogens will decrease. But this was more of a multiple choice. If you're asked for part 2s and you have to write out your answers, let's look at some of the answers that are acceptable. If they say catalyst or increasing surface area of a solid, you can write has no effect on equilibrium. If you see solids in the substance, like we said, just solids are added, you can also say, again, that has no effect on the equilibrium. However, equilibrium can produce more solid. So think about saturation. At some point, the sugar won't dissolve anymore in the water and it sinks to the bottom. And no matter how much sugar you put in, it's already saturated, right? So it's going to float, it's going to sink to the bottom, sink to the bottom, sink to the bottom. And so it doesn't matter if you're adding more solids. Solids don't affect that equilibrium saturation condition. However, if I heat the water up, I have now changed it. According to LeChatelier's, it should shift in a direction, right? If I heat it up, it will dissolve more. And so the solid will disappear. So you see how equilibrium affected the solid? Or if I cool it down, more solid will precipitate out. Again, the solid gets affected. Addition of the species X. What you should say is additional X will result with Y. We react with Y or shift in this specific way towards the other side, forming something or removing something. So you should say something about what it's colliding with and what it's forming. If you're removing a species, you should say something like, removing this species will force the reaction to shift towards that own species, the same species, to restore it, thus increasing blah, 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 and decreasing the substance, right? Increasing pressure and decreasing volume. Either way, these are opposites, but they're actually doing the same substance, the same change. A reaction with a lower volume will factor the side with less moles, thus increasing this side because it has less moles, or decreasing this side because it has more moles, or shifting to the reactants or products, depending on what type of question you want to answer. Increasing the temperature. You should write something like, increasing the temperature favors an endothermic reaction, thus favoring forward or reverse. Or you can say it decreases this by reacting with this, increasing this, decreasing that. So notice that it's not enough to just say shifts right. You have to say it collides with this to form this, or it restores this by using this, right? A little more detail about exactly what's going on. So for the last part, we're going to do some more difficult examples where I want a full explanation. Again, if you want to pause the video and try them on your own, that might be smart. So we want to know which way the reaction should shift. A lot of people know that addition of lead doesn't seem to affect the equation. You might say no effect. But the lead ions will take the chloride ions out and precipitate out PbCl2. So in that case, chlorine is being removed. A lot of then students, who notice that, might just say shift right. But we want to be more clear. So PbCl2 will precipitate out, chlorine's removed, and the reaction shifts right. Notice it's a little bit more clear. Addition of sodium chloride, as we saw in a previous example, means we have more ions. The more ions will not necessarily affect the equilibrium because it's going to already be set. And again, the solids do not affect equilibrium. And similar, pulverizing the sodium chloride so it has more surface area. It might make it go faster, but the same amount of salt will dissolve in that water, right? It's not going to dissolve more. It just will dissolve it faster. And then in this one specific for oxygen, how is oxygen going to change with these? Addition of an inert gas. The inert gas is just going to take up room. It's not going to actually do anything, and it's going to affect all of them equally. So I don't think it's going to interfere at all. Addition of helium at a constant pressure. In that case, now it's taking up room, and you can't do anything about it. It's not like a balloon that moves. It's taking up room, and now they're all a little bit more confined. If you're confined and there's something taking up their room, that means they have less volume, and you're going to favor the side with less moles, which is the left side with only 2 moles. In that case, if water is being formed, then oxygen has to be removed, right? So helium takes up the space in the reaction chamber. Therefore, if the volume decreases for the remaining gases, the side with fewer moles increases and oxygen decreases. So it had to stay constant pressure in order for the helium to have an effect. Otherwise, it doesn't react with anything. And then removal of oxygen means we're taking out oxygen as it forms. The reaction will shift forward to restore oxygen because it doesn't think that it has any. And overall, the amount of oxygen you're going to be left with will decrease because what you removed will never get fully restored, right? So in the chamber itself, not where you're putting it, but in the chamber itself, it will never form as much as you used to have. So back to the question in the video, how the heck did they make phosgene gas if it's so hard to make and its Kc is so tiny? So some things like decreasing the temperature, because if you take out the 6 kilojoules of heat, it will shift to the right to make phosgene. Increasing concentrations of CO and Cl2 might help make more phosgene, or taking out phosgene as it's formed will all shift these reactions to their products. At this point, you should be able to use LeChatelier's principle to determine how a reaction will change to restore equilibrium.